So I put the little notation here that we should assume that 3, -20 is a point on the graph, just because it's such a really absurdly zoomed out graph that it's kind of hard to tell what the accurate points are. Like if you wanted to try to eyeball it, it wouldn't be the easiest thing in the world to do, right? So if you look at the points here, honestly, I'm not even 100% sure why I have the 3/2 there. So let's just ignore that. So looking at the points, hopefully you recognize that there are 3 distinct roots. And we define a root as the same thing in terms of functions, the same thing as a 0 of a function, also the same thing as an x-intercept. All right, so an x-intercept and a root really essentially in this context mean the same thing in 2-dimensional mathematics. All right, so and that's where we're living for essentially the whole course. So it won't be until you get to so higher levels of calculus before you expand beyond 2 dimensions. So but the rules are, for lack of a better term, rooted in what we're talking about now, but they will just branch out to cover more concepts. So when I say something like a root is an x-intercept, that's true to an extent. It only works that way in 2-dimensional math. All right, so fun fact of the day, I guess. Here I'm looking at the behavior around that first root. All right, so I'm going to draw a line because I can. All right, around that root. This looks an awful lot like a line. All right, so it looks like a line. Around the root x = 0. All right, the key ingredient there is that we're talking about a line. All right, so the characteristic, the relevant characteristic of a line here is that that is a first-degree equation. A line is a first-degree. We could say equation, but we're really focusing on polynomials, so I'll say polynomial. So it looks like a line around that point, and a line is a first-degree polynomial. All right, I'm gonna skip over the second root for a second because I want to kind of go in order of powers here. Around that this point here at 2, 0, we're looking at something that looks kind of like a parabola. All right, so it looks like a parabola.
Professor, I'm sorry, did you post this worksheet as well? Because I just can't find where it actually is.
Yeah, it's in class notebooks. If you go into course content. So if you go to course content, class notebooks, you'll see unit 2. That's what we're going for.
Thank you. I was in the wrong tab. Thank you.
Yeah, no problem. So it looks like a parabola around the root. X = 2. A parabola is a second-degree polynomial. All right, so it looks like a parabola, and a parabola is a second-degree polynomial. All right, I'm just going to kind of chuck that in over here. Very important that you take note of what type of polynomial the behavior is represented by around a root, because that gives you what's known as the multiplicity. But more on that in a minute. We got a green one here. So this one, this is the unique one, because depending on your experiences in previous courses, you may not really know too much about higher order polynomials. But I can tell you that if you were to graph the function y equals x cubed, or the function y equals negative x cubed, it has a unique behavior. So unique compared to a line and unique compared to a parabola, right? It's a third different type of behavior that you could have around a root, right? So you'll see that in one instance, it increases, levels off, and then continues increasing. And in another instance, it'll decrease, level off, and decrease. Right? That's what's happening here around this other point. If I could actually draw without like shaky handwriting. One of the drawbacks of nerve damage, but fortunately I have the app that smoothed it out a little bit. Now, it's not picture perfect. I mean, even the pre-printed graph wasn't picture perfect, but it does have that same behavioral characteristics or characteristic where it's decreasing, leveling off, and then decreasing again, right? Just like a cubic function would. So it looks like a cubic around the root x equals 1, a cubic is a third degree polynomial. Right? The behaviors of the roots can always be classified as one of these three different possibilities. So you might look at it and say, well, what about a fourth degree polynomial? I'll show you real quick. If I say y equals x to the fourth, that behaves an awful lot like a quadratic. Right? I could say x to the sixth, still behaving like a quadratic, just a little flatter at the bottom. Right? X to the eighth, 10th, all those even powers, they're at heart, their behavior is similar to that of a quadratic. Right? A cubic has a similar behavior to a quintic, 5th degree, 7th degree, 9th degree, all those odd powers. They all are rooted, or at their heart, they have the same characteristics as a third degree polynomial. So they have the same behavior. What that allows us to do is give each one of these what we call a multiplicity. All right, the line has a multiplicity of 1. So a multiplicity of 1 because it's a first degree polynomial. The cubic has a multiplicity of 3 because it's a third degree polynomial. And the quadratic case, or the parabola case, is multiplicity 2 because that's a second degree polynomial. Right? So if you know those three cases, then you're going to be in pretty good shape. Now, we still haven't talked about that assumption that I wrote on the top, assume that 3 negative 120 is a point on the graph. I'll get to that in a minute. Right? That information has to be given to you for a problem like this to work. So it's not something that I'm expecting you to assume. I'm telling you that assumption will be made. It'll be like on a test, it'll say, suppose 3 negative 120 is a point on the graph. Right? So what we would do here is we would write our polynomial p of x. You know, normally we'd say f of x, but p for polynomial, it just kind of makes sense. When we talk about rational functions, we say r of x, r for rational. All right, that's fine. I mean, you could say f of x. I'm not going to take off any points for anything like that. So, you know, just keep that in mind. But we're going to have some multiplier k, some unknown multiplier, because if I say x to the third power is the behavior of my graph, for example, around that point, somebody else could come along and say, well, what about 0.5 x to the third power? They behave exactly the same way. one's just a little wider than the other. So we have to allow for different coefficients. So the way we do that is by putting a coefficient of k. Then what we do is indicate all of our possible roots, but in factor form. All right. So we have 3 roots. So that means that 3 unique roots, which means that we're going to have 3 corresponding factors. All right. So our root here is x equals 0. Our root here is x equals 1. And our root here is x equals 2. And again, the root is just another way of saying, in this context, is another way of saying x-intercept. So the x value of where it crosses the x-axis. All right. If I want to find the factors that correspond with those roots, what I would do is solve those equations. Instead of solving for x, I'd solve them for 0. It's kind of a weird thing to think about, but basically it's just telling us get everything over to the same side of the equation. Anything that involves a variable or a non-zero value, get everything over to the left. So for the first equation, that's already done. I got 0 alone on the right, everything else is on the left. But for the second one, I'd subtract a 1 from both sides and get x minus 1 equals 0. So again, the whole idea is that when I say solve for 0, that all that's saying is get 0 alone on one side of the equation. Right? Doesn't really matter which side, preferably on the right-hand side. Right? So then I would do the same thing with the x equals 2, subtract the 2 from both sides. I want to do that in blue, actually. And we would have x minus 2 equals 0. And that's the same deal. We solved for 0. We got 0 alone on the right-hand side of the equation. All right. Whatever is on the left side of those equations, those are the factor form corresponding with those roots. Those are what go in the parentheses. So I'd have x. Oops, I'm going to go black for this one. X minus 1, x minus 2. All right. Now the multiplicity tells us the powers. All right. So we would indicate the power for each of these based off of the multiplicity of the roots. All right. So we have multiplicity of 1 for the first one. So just tuck in a little 1 here. 3 for the second one. And 2 for the last one. So 1, 3, 2 would be our powers. All right. It takes a little getting used to, but that you'll find as you go forward is actually kind of the easier part. Because once you become adept at identifying the roots and identifying the multiplicity, then you'll already know the expressions and the corresponding powers. But what we need to do, well, we got to do a couple things. We have to determine the k value. We also need to be prepared to expand this whole thing out, right, using distributive properties. So that last part is not very entertaining, to say the least. Right, but if I tell you to assume that 3, negative 120 is on the graph, what that's telling me is that there's some value x on the graph that corresponds to p of x as its y value. Right, so that tells me that I can replace every x with a 3, and the p of x I can replace with a negative 120, and then I could use that to solve for the value of k. So I say negative 120 is equal to 3 instead of x to the first, times 3 minus 1 instead of x minus 1 to the third, and then 3 minus 2 instead of x minus 2 to the second. Simplify. K times 3. 3 minus 1 is 2, cubed is 8. 3 minus 1 is 1. Sorry, gave it away. 3 minus 2 is 1. squared is 1. The right-hand side here becomes 24k. And if I want to get k alone, I would just divide both sides by 24. All right. So I'd be looking at -5 as the value of k. So what that would give me is a factored form of an equation that should, in theory, map out the same graph that we were given on paper. In theory. We'll see in a sec. All right. So, and there are other ways to kind of, I'd say, troubleshoot or use a trial and error approach, but they're not exact, so I tend to not even bother with that. But what I would do here is type in this function that we just determined to call p of x, let it equal -5 times x minus 1 x cubed. Oops, I lost my 1. And then x minus 2, close it up, square it. You look at this graph and compare it to what's on paper. And if it looks the same, then you're probably in business. If not, then there's probably a mistake somewhere. But, scaling and the zoom, that could play a role in your interpretation. But it does look pretty okay because it has all the same characteristics. At 0, 0, 0, it looks like a line. At 1, 0, it looks like a cubic. And at 2, 0, it looks like a parabola. The only question is 3 -20 on this line? So what I would do is I type in P of 3 and make sure it gives me a -120. And if I do that, then I'm in pretty good shape. I feel confident that this is correct. I mean, you could, like I said, play around with the zoom a little bit, make it a little shorter. This one, I mean, it's kind of hard to tell, but it goes as low as -6, as high as 2, -0.5 to 2.5. So you can make your domain and range similar, if not exactly the same. And see what it looks like. Yeah, it looks pretty good. Looks pretty spot on. So at that point, you'd be pretty confident that you did everything right. Okay. So then that brings you to the part of the process where you'd look to expand all this out. Okay. If you got to do that by hand, it's not fun, but it is manageable. Right. The powers are low enough.
I'm sorry to interrupt you. P of 3, when you type it into Desmos, I'm taking notes on that. Y of 3, like what made you pick the number 3?
Because that's what they told us the coordinate was.
Okay.
They gave us the x value of 3.
And it should equal -120 when you type it in.
Exactamundo. So the powers are low enough here that you wouldn't consider doing something like Pascal's triangle to expand it out. This is more like, right, you just kind of strap in and get to work, So I'd look at this as, all right, I got x minus 1 times x minus 1 times another x minus 1. Then I have a couple of x minus 2s, and you distribute them against each other 2 at a time. All right, I would hang on to these two, the -5x, for later in the game, because there's really no benefit to multiplying through with that just now, because that's actually one of the easier things to do. All right, so what I would do is multiply this by this, x squared, outer -1x, inner -1x, put them together in -2x. -1 times -1 is +1. Then everything else comes along for the ride. Then I would distribute this trinomial against the next binomial, you know, it gets a little crazy before too long. So you find yourself moving on to separate paper and all that stuff. But you know, if you take an organized approach, it's not terrible. It's just very tedious. And so I multiply through with an x squared to each term here, x cubed minus x squared. Then I would multiply through with a negative 2x, so negative 2x squared plus 2x. Then I'd multiply through with a positive 1 to each term, so plus x minus 1, then combine it all up. So x cubed minus 3x squared plus 3x minus 1 would be my result for that part of it. Right? So it's already starting to kind of get a little spicy here, but it is manageable. Now you might look at it and say, all right, I'm going to multiply through the x minus 2 and then another x minus 2. That's up to you, but I have a tendency to look at it and say, let's take care of these two, because that's just regular FOIL, and then take the results and multiply. All right, so x times x would be an x squared, outer negative 2x, inner negative 2x, giving us a negative 4x plus 4. So then I would use, you know, sort of like that I'll call it procedural method, but it's really kind of like a, you know, a one step at a time sort of thing, where you just kind of look at it and say, it's systematic more than anything else. I'm taking this x cubed and multiplying it by each term. Then I move down the line to the next, well, it should be the negative 3x squared multiplied by each term. If you go systematically through, it tends to be a little bit easier. But you got to be careful with your algebra, because one little mistake will have heartbreaking consequences down the line when you go to check your answer. All right. So x cubed times x squared, keep the base, add the exponents, becomes x to the 5th. X cubed times negative 4x is negative 4x to the 4th. X cubed times 4, that's the easy one, plus 4x cubed. And then move on to the next term. Right. Negative 3x squared times x squared is negative 3x to the 4th. Negative 3x squared times negative 4x would be positive 12x cubed. Negative 3x squared times 4 would be negative 12x squared. So it gets a little easier as you work your way down the line, because the powers get smaller and smaller, but that doesn't mean it's ever going to be easy. It's still systematic. You still got to be careful. Right. So when I go through multiply with the 3x, I get 3x times x squared, which is 3x to the 3rd. 3x times 4x is negative 12x. 3x times 4 is, I'm sorry, negative 12x squared. They almost screwed it up. 3x times 4, that's going to be my 12x. And then I still have to multiply through with the negative 1. I'm just going to smidge all this stuff over a little bit. Get a fresh new color. I'm going to go red for those keeping score at home. I'm going to multiply through with the negative 1. Negative 1 times x squared is negative x squared. Negative 1 times negative 4x is positive 4x. Negative 1 times 4 is negative 4. We want to combine our like terms. And when we do that, things will clean up a little bit, but we don't want to lose sight of the fact that we have to multiply all this by negative 5x in a couple of minutes. So, but a little highlighter action never hurt anybody. Let me get a fresh new one here. I'll go back to yellow. Pretty tricky standard actually. So x to the fifth, there's no counterpart to that. We don't have anything that's like an x to the fifth, but we do have stuff that's like x to the fourth. So when I write my solution here, or part of it anyway, x to the fifth, and I'm going to have negative 7x to the fourth. Just combining like terms. I'm going to get a new color. I'm going to go with a light blue. No, I've already had a light blue. Go with a light orange. I want it to actually look somewhat orangey. So anything with a power of 3 would get combined. So positive 4 plus 12 is 16, plus another 3 is going to give me a 19. So positive 19 x to the third. Then I'm looking at my powers of 2. Negative 12 minus another 12 is negative 24, minus another 1 is negative 25 x to the second. And then we're kind of in the home stretch, although this is like the home stretch of a marathon rather than like a 5K. But we'd have the positive 12x combined with a positive 4x, giving a 16x. And the only thing left would be the negative 4. But again, we still have to multiply through with that negative 5x. But once we do, we'll have our answer. So that's good news. Right? So we're looking at negative 5x to the 6th plus 35x to the 5th minus the 95x to the 4th plus 125x squared minus 80x. Oh, sorry, I lost my powers. This would be a power of 3. So negative 5x times the negative 25x squared to become 125x to the third, and minus 80 x squared, and then finally plus 20x. All right, so in theory, that should give me the exact same graph. But there's so much algebra there that it strikes at your self-confidence, or at least mathematically anyway. There's so much algebra that I probably made a mistake. So you kind of go in with that expectation, prepare for the worst and hope for the best. And if it works out, you're a happy camper. If not, then you go looking for where the mistake happened. They'll just typing away. And the hope is, oops, undo. It's the beauty of the undo button. The hope is that the mistake isn't you typing in something incorrectly, right? Because that's always a possibility. All right, and so I finally got the equation in, and you'll see now that it's mapped directly on top of the points for the purple graph, which was the one before I simplified. Right? If you're not sure, then you can make the line a little thicker. If you long press on the graph icon on the left-hand side, long press on that, you'll get this menu that comes up. You could change the style of graph, and you could change the thickness of the graph. So instead of being a thickness of 2.5, I'll make it like a thickness of 5, so thicker, right? So that when I tap on the other one, I can see that they're both mapping to the same location a little bit more clearly, right? You'll also see that now we have an error for the P of 3. It's like, oh, we did everything wrong. P of 3 is not giving us negative 120. We didn't do anything wrong. It's just that Desmos is like, all right, well, which P of X do you want me to plug into? You gave me two P of X functions. So one way to handle that is to not write this one as P of X. Just call it Y. And everything will work out, you know? Because we're really just typing it in the second time to verify that you didn't screw up the algebra. So it's really up to you in terms of how you type it in. Y equals f of x equals, you know, q of x equals. It really doesn't make a difference. All right, but that's a pretty juicy problem. But you could see here that this is all, you know, it's I don't want to say it's memorization, but it's kind of closer to that than it is just you know, procedural skill. Like if you could identify the roots and the multiplicity, then you can set up your equation. If you know a point on the graph, then you could solve for k. The thing that'll bog you down is the algebra. It takes a little while to do, but you know, that's part of the fun, right? So I wanted to hop down and tackle number 3 on page 22. Just going through the process that talks about finding intercepts, symmetry, multiplicities, behavior, and all that good stuff. It's a whole lot easier to go this way than it is to go the other way, because you have the benefit of using a calculator to help sort of, I'll say check your work, but it's more like you could use a calculator to know what the answer is supposed to look like. You just have to make the work justify your answer. All right. So when it says sketch a graph, it's not always going to be as simple as just drawing the sketch of a graph. If I ask you to justify by including different characteristics, you got to be prepared to do that. So those different characteristics would be x, y intercepts, symmetry, and so on. Okay. So first off, x and y intercepts, those are pretty easy to do. They're very procedural. Right. So if I want to find the x-intercept, well, one of them is easier to do than the other. Right. So the x-intercept, set the equation or the function equal to 0 and solve. All right. So that would be 0 equals -2 parentheses x plus 3 cubed times x minus 5 squared, and you would solve that equation. All right, since it's already in factored form, it's actually pretty easy to do because you don't have to go through the process of coming up with the factors. I'm going to show you some situations in a little bit where you will have to factor the polynomial to get it in this form so that you could then do all this other stuff. A little bit more challenging, but still also doable. All right. The zero product property from college algebra, even before that, tells us that if you have an equation in factor form and it's set equal to 0, you set each of your independent factors equal to 0. And solve. All right. You might wonder what happened to that -2. You can put that -2 wherever you want. If I put that -2 right here, the first thing I would do is divide it out. It would cancel completely, and you would just get what you would get if you had ignored that -2 to begin with. All right. So it basically tells us that if you have a coefficient, a non-variable coefficient, you just drop it. It's going to cancel away anyway. I could have put that -2 on the x minus 5 squared and it would have been fine. All right. Now, if I want to get rid of a power of 3, I take the cube root of both sides of an equation. All right. The cube root of the power of 3 cancels out, gives us just an x plus 3. Cube root of 0 is 0. then I would solve for x by subtracting 3 from both sides. All right. But this actually has us kind of working backwards from what we were doing before. And that is to say that this root corresponds with a factor that's raised to the third power. All right. If a factor is raised to the third power, it behaves like a cubic around its x-intercept. All right. So this is a multiplicity 3 situation. All right, so whatever the power is of your factor will correspond with the multiplicity, which in turn would correspond with the behavior of the graph around that x-intercept. All right. In the second, or in the case of the second factor, all I'd have to do is take the square root of both sides there. X minus 5 equals 0. Add 5 to both sides, and you get x equals 5, but that one corresponded with a power of 2. So this is going to be a multiplicity 2. So we're going to hang on to this information. We're not going to graph anything yet because we got more stuff to come up with. But we're going to hang on to this and use this when the time comes to create the graph. But before we do that, we're going to figure out the y-intercepts. Right, finding the x-intercepts that was pretty involved. That process is not short and sweet. But the process of finding y-intercept is actually very, very simple. All you have to do is compute f of 0. Which is really telling you to replace all the x's in your original function with a 0 and simplify. All right, like so. So everywhere I have an x in my original function, I replace it with a 0 and simplify. So I got my -2, 3 cubed, 0 plus 3 is 3. Cubed is going to be 27. 0 minus 5 is -5, but -5 squared, -5 times -5 is positive 25. Okay. So we'd have to multiply this out, but it'll give us our y-intercept, which is actually going to be pretty substantially large. But it'll give us a clue as to how we should scale our graph. So it's beneficial to know this. All right. So 25 times, I know 25 times 25 is 625. So I got to tack on another couple of 25s. It gets me 675, and then double that, 1350, I think. But yeah, you don't have to do it in your head. So negative 1350 would be my y-intercept. Right, so that means I got to go down. In order to find my y-intercept, I got to go down 1,350 units, or scale my graph so that I don't have to go down that far. Right. But that's a different conversation. So then we get into symmetry. To assess symmetry, we also, well, in the same breath, we are also assessing the even and oddness of a function. All right. So for symmetry, we're going to assess whether the function is even or odd.
Professor, before we continue, can you just quickly explain the multiplicity, how you found it was 3 and how you found it was 2?
whatever the power is of in your polynomial of the factors.
Okay, so it was to the third, so it's the third, it was to the second, it's the second. Okay, thank you, thank you.
No problem. All right, so we assess whether, for symmetry, we assess whether the function's even or odd. This goes back to the previous unit. We compute f of negative x, which tells us to take our original function and replace each x with a negative x and simplify. All right, and this is also kind of, I mean, I don't want to say it's an archaic topic because it's not. There's value in knowing how to do this stuff by hand. It's just, it goes back to what I've been saying all along, where depending on where you end up mathematically, if this is the last math class you'll ever take versus, you know, if you're going to be going down the calculus road for the next couple of years, you'll experience different things. Bottom line is, it's kind of hard to look at this and say that it's valuable at this point when you can just type the original function into the calculator and see whether it's symmetric. Right? And the only thing I could say about that is there may come a time down the line where you need to know this in your calculus classes. Right? So just remember, if a function is even, it's symmetric over the y-axis. If it's odd, it's symmetric over the origin. Really symmetric through the origin. So I'd have to simplify this and see if I get something that's exactly the same as what I started with, or something that's exactly the opposite of what I started with. All right. So we got to simplify. Always got to simplify. So -2. We got my parentheses cubed and my parentheses squared. Inside that first set of parentheses, I have a -x plus 3. Right? From that, I can factor out a -1. So I'm going to write it as -1 times x minus 3. All right. So all I'm doing is dividing each term by what I'm creating as a GCF of -1. Right? The whole idea here is to make that x positive again. And so mission accomplished. I just got that loose -1 hanging out there in the middle of nowhere. But I can rewrite this now, and we'll get to the binomial squared in a second. But I could rewrite this as -2 times -1 cubed times x minus 3 cubed. Okay. So all I'm doing is factoring out a -1, and you can verify if you're ever unsure about something, whether it's something like this or even, you know, a numerical property. Just pop it into Desmos and see if it's a true statement. Like -x plus 3. I look at that and I say, well, I'm not really sure, but I think that's equivalent to -1 times x minus 3. All right, so I'll type in -1 times x minus 3. They create the same graph, so you're confident that they're equivalent. All right? So that's a little nifty way of checking your work. You know, it won't bring you down this path to begin with. You'd have to come up with the idea to get yourself started, but it's something that will help you kind of verify that your idea is a valid idea. Right? Same idea for the negative x minus 5. So I can write that as negative 1 times x minus 5, which in turn would become, if I take that negative 1 and square it, negative 1 squared and x minus 5 squared. All right, so I'm looking at what I have here. That negative 2 is still a negative 2. Negative 1 cubed is negative 1. I got x minus 3 cubed. Negative 1 squared is a positive 1. And x minus 5 squared stays put. All right.
I just have a question.
Hey, Professor.
Sure.
Is it supposed to be x plus 5? Or,
Oh, thank you.
yeah.
Appreciate it. Boom, boom, and boom. Thank you, thank you. So then when we clean it up, and this would be the last step because there's really not much you can do after this. I'm just going to take all those coefficients and multiply them together. And when I do that, I get positive 2 x minus 3 cubed x plus 5 squared. Right? And so now what we want to do is compare this to the original function. Right? So I'd say, is this the same as f of x? Or is it opposite?
Opposite.
Very close to being opposite. That x plus 5 throws everything off. All right. So if it's the same, it would be an even function. If it were opposite, it would be an odd function. But we look at the coefficient, really, the only thing that would determine whether it was an opposite is whether the only thing that changed from the original function was that the negative 2 became a positive 2. But everything else remained the same. You look at the minus 3 and the plus 5, and you're like, oh, everything's opposite. This is great. But that's actually not the opposite of the function, because if you negate a function, you really just multiply it by negative 1. Right? So in order to make an opposite of f of x, all I would need is the same thing as f of x, just with a positive sign as my leading coefficient, as opposed to a negative sign. Right? And this is what I was saying before. If you're ever unsure, you can go to Desmos and have a look. So we just worked through this algebraically, and I'm saying it's neither. It's not exactly the same, and it's not exactly the opposite. So I'm saying it's neither, which is telling me that there is no symmetry. Right? So there's no symmetry. All right, but we can verify that by looking at the picture. Negative 2, x minus 3. The original function was x plus 3 cubed times x minus 5. Close it up, square it. I mean, this is a funky looking function, all right. But the one thing I'm not seeing is symmetry. All right, it does not look like it's exactly the same to the left and to the right of the y-axis, and it doesn't look like if I took any point and flipped it through the origin that I would get another point on the graph. So we're not looking at anything that has any kind of meaningful symmetry here. All right. So those are really the important pieces of the function, but the last thing that we would talk about when it comes to creating an appropriate graph would be the behavior, the end behavior of the graph. All right. So that would be really D or E, really it's all kind of a combined thing. But the end behavior of the graph is determined based off of the power. the highest power of the function. Right. So if I were to expand this out, and the whole point behind this is to not actually have to expand it out. It's more so that you would think about, okay, what would happen if I were to expand it out? Right. So I would have something, this would be a power of 3. If I distributed the whole thing out, this would be power of 3. If I distributed this out, this would be power of 2. If I multiplied those two powers, keep the base, add the exponents, my final result would be a power of 5. All right. So the combined power would dictate the end behavior. So end behavior, because we're dealing with a power of 5 polynomial, if you were to look at just an ordinary x to the 5th graph, so we'll just type in y equals x to the 5th, it behaves the same way as x to the 3rd, all right? Starts low, ends high. But if it's negative, if the leading coefficient's negative, starts high, ends low, all right? Now I use the verbiage of, all right, well, yeah, as x approaches negative infinity, y approaches infinity. That's the same as saying starts high. All right. What that means, I mean, notation-wise, it's a little funky, but what that's telling us is that if you go to the left forever, you'll go up forever. And that's pretty consistent with what you see in this graph. If I keep going left, I keep going up. As x goes to positive infinity, y goes to negative infinity. Ends low. All right. So if I keep going out to the right, I'll keep going down. All right. So, we have the mathematical way of saying it, which is the arrows and the infinities, but really it's like it starts high, ends low, or it starts low, ends high, starts high, ends high, starts low, ends low. Those are your different possibilities. As long as you have an idea of what these, the basic graphs look like, which really come down to the 3 basic graphs I was talking about before: the linear, so the line, the parabola, and the cubic. Then anything else would behave like one of those graphs. You pretty much have what you need as long as you have a good understanding of those particular graphs. Right? So I know that this one's going to start high and low. It's going to pass through x values of -3. I'm sorry, -3 and +5. At -3, it's going to have a multiplicity of 3, so it's going to behave like a cubic. At 2, it's going to behave like a parabola, and it also has to go through the y-intercept of -1350. That's extraordinary, right? So when I go to create my graph, you got a lot of wiggle room when it comes to curve sketching. I want to give myself a lot of room on the low side, but I also want to scale my graph substantially. So x, y, I'm inclined to go by like 500s, right? So -500, -1,000, -1,500, -2,000. You can go further if you want, but I think that's probably sufficient. Now, in terms of the x-axis, I think I could go by 1s there because my roots they're nice convenient values like -3 and +5. So I'm just going to go by 1s here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. If you're only going by 1s, you don't have to label anything. It's when you're going by something other than 1 that you have to label it. Right? So I know that I'm going to have a y-intercept that's around negative, well, it's exactly around at negative 1350, but it's going to be in the neighborhood of the negative 1500. So I'll just kind of eyeball that. I know that I'm going to have an x-intercept at negative 3 and a positive 5. And this graph has to start high and low. All right. So in order for that to work, and also behave like a cubic at this location. So, you know, just kind of put the behavior in. So this one's got to be like, let me get that a little thicker. Let me go with red here. It's got to behave like a cubic. The only way that it would behave like a cubic and still be able to fit the points that are here would be if it were a negative cubic, right? Instead of a positive cubic, right? And we want it to start high and low, so that makes sense, right? We also need to behave like a parabola around this point. So we get our multiplicities in there. Then we just kind of piece the rest together where we say, okay, it's got to start high and low. All right, start high. All right, it's got to grab this point over here. So I'll just do this, and I got to figure it's got to turn around at some point over here, right? So I'll just do that. I'll just turn it around. Yeah, maybe go a little bit lower. And then it's got to end low. Yeah. And it doesn't have to be perfect because this is a curved sketch that's only taking into account the important features. All right. So as long as you know what the behavior is around the roots, the end behavior, the symmetry was really, I'd say it wasn't as necessary. It just was, it's nice to know. But based off of this information, we have what we need. And so, like I said, it kind of feels like an archaic topic because we could just put the original function in and see what it's supposed to look like. I already had it in, but I deleted it for whatever reason. You know, at first glance, you're like, wow, this can't be right. Look at what we have on paper compared to what's on Desmos. But then, you know, you realize you're scaling it down to like negative 2000. So let me get, you know, tap on that little wrench, change my y-axis to go from negative 2000. And then I'll make it go to like, I guess, 500 just to keep it sort of reasonable. And I only went from negative 5 to 5 on the x-axis. So it's really in this neighborhood where I'm just kind of guessing down around here. Because I don't know what that turning point is. And, you know, this one, I could grab it from Desmos, but that's sort of cheating. You know, really, I wanted to graph it based off of the information in the directions, or asked for in the directions. But this is the only part that I would really be guessing at. And I honestly, I think I didn't do terrible in terms of my guessing. Yeah, I could have gone a little bit lower, but that's not a big deal. And it's not the kind of thing that you would lose credit for because that's not the point of this exercise. Right? It's to come up with a reasonable sketch of the graph based off of these other calculations. All right. You might find this hard to believe, but eventually, you know, the further you get along in math, the more, I'll call it an expectation, but it's really more of a hope that you'll be able to, through these kind of experiences, be able to look at an equation and have a sense of what the graph looks like just by looking at the equation. You know, it's like, oh, I know this because, you know, like you'll see the powers. You're like, okay, I know that it's a fifth degree polynomial. It's got to start high and low, or start low and high. Right? It's going to have a turning point here. It's got multiplicities there. And you just have a sense of what the graph looks like rather than having to sketch out the whole thing. All right. So that's the review. That's what we were supposed to have covered last week. But we're going to go on to synthetic division now, which is actually a really interesting topic because it allows you to factor polynomials that are more than degree 2 polynomials. So, you know, like in the past, you've factored quadratics, you know, you use different methods for that. Maybe you completed the square and things of that nature. But now what we're going to actually do is focus on higher degree polynomials using what's known as a synthetic division process. I'm going to skip this do now problem on page 23. We'll come back and review completing the square at a more appropriate time, but I wanted to get you to the concept of synthetic division first. All right, it's very procedural, and it's the type of concept that a lot of folks will get annoyed at because there's little to no explanation as to why it works. It's more of an explanation of how it works and just the belief that it always works, right? And so what it'll allow you to do is divide two polynomials as long as the denominator or the polynomial you're dividing by is or can be represented as a first degree polynomial, meaning a linear polynomial or a power of one polynomial. I know I said polynomial a lot there, but if you're looking at this expression here, you see that there is no power higher than one, right? That's what we're looking for when we have synthetic division. If you're dividing by something that's got a higher power than one, then you'd want to simplify that first before you start using any synthetic division, right? But what we would do is take the polynomial that we're looking to divide and arrange it in decreasing power order if it isn't already in that form. So I'll just kind of accentuate that relationship. We have x to the, I almost said that, x to the second minus 5x minus 12. That's really the same as saying 1x to the second minus 5x to the first minus 12x to the 0. You'll notice hopefully that every power is included there from the highest power in the polynomial, which is power of 2, all the way down to a power of 0 without skipping any powers along the way. All right. So, and I'll show you an example in a few minutes where you'll have to kind of fill in the blanks, but we're not there yet. So just kind of sit tight on that. Sit tight on that. Write the coefficients. All right. So it might feel like I've already done that, but what I mean by that is strip this down to only the coefficients. All right. So I would rewrite this, ignoring the x's. Now that I have it in the appropriate order, I would just ignore the x's and write it as -1, 1, -5, -12. All right. Only the coefficients. Now, the next step, so we've done step 1, 2, we're on step 3, write the constant r of the divisor. So this is the divisor here. The constant r of that divisor, all right? So the divisor will be in the form of x minus r. We just need to identify what that r value is, all right? It's a pretty easy way to do it. Well, there's two ways. One way is procedural, the other way is just more intuitive. You could set them equal to each other. X minus 3 equals x minus r. Solve for r, the x's would cancel. You'd have -3 is equal to -r, which means that 3 is equal to r. You do it that way. But what a lot of people prefer to do is just look at it and say, oh, well, it's the opposite sign of whatever the constant is at the end. It says -3, so I'll just grab the +3. Most of the time that'll work, except when the coefficient of x is something other than 1, then you get a little bit of an issue. But this technique, this algebraic approach will always work. So I find a lot of people kind of default to that. Even if they know the other way, you know, just pulling out a number, they're like, I'm not going to take any chances. I'll just do it this way. No, what we're going to do is write a little, kind of like an L bracket. It's supposed to be a fraction bar, but if you're not familiar with synthetic division, then you've never seen anything that Oh, I mean, unless you've done some everyday math back in the day, but you're probably not familiar with division bars that look like this, but you know, it's possible. I'm just trying to think. Just thinking of a good word of the day. We'll go with exceptional. The word of the day is exceptional. So once again, the word of the day is exceptional. So what we're going to do is we're going to take that R value.
Oh wait, Professor.
Sorry.
I don't know how to spell that word.
I mean,
How do you spell
You-
exceptional?
you could try to Google it.
Autocorrect. Autocorrect.
Uh,
Oh my God, thank you.
Okay, so now we can't use that word. Sorry, we're kind of missing the point of the word of the day. So yeah, I understand that the spelling was an issue, but now there are people who are probably not paying attention who now know what the word of the day is, and so now they have access to it, and it defeats the purpose. Right? So yeah, so that's no longer the word of the day, folks.
I'm sorry.
Oh, that's all right. We'll do a different one in a few minutes, hopefully, if I remember. So the R value goes on the outside of the bracket. All right. So we just kind of throw it on the outside there. It's kind of a weird procedure, but it is what it is. All right. So what you're going to do is you're going to take whatever that leading coefficient is, and you're just going to bring it on down and write it here. All right. So we have that number 1. We just bring it on down and write it at the bottom of the that fraction or division bar. Fraction, division. I don't know. I'm making stuff up now. Then, and this part is very strange. So you definitely want to follow along with this. And I'll repeat it a couple of times, but you got to make sure that you understand, because like you see the steps written there, and the steps are probably the best. I mean, I got this from some online resource. This is the best explanation I've seen for synthetic division, but it still doesn't always get the job done. What you do is you take this number, whatever this number is, you pull down that leading coefficient and you multiply it by the outside, whatever that number is on the outside. All right, so 1 times 3 will give you a 3. That result goes here. All right. Then what you do is you add down the column. So I'm going to take that -5 and I'm going to add to it a 3, and that's going to give me a -2. All right. You're always going to add down the column. All right. So you will then take that number, multiply it by the number on the outside, and put that result here. So we'll make result the word of the day. Result. So -2 times 3 will give you a -6. Then you're going to add down that column. All right, so you're always adding down the columns. -12 plus -6 gives a result of -18. All right. I'm going to do this process again with another example in a minute, but you're adding down the column, multiplying by the number on the outside, which in turn gives you the next entry in the table. Add down the next column of the table, and then from there you just keep going until you complete the table. So then it begs the question, all right, so what did we accomplish by doing this except torturing pre-calc students, right? Well, what happens is we took a quadratic. In this case, it's power of 2. Right, it was a power of 2 equation, and we've divided it by something that was power of 1. The result is going to be power of 1. Right, so what we do is we look at the original power. All right, whatever we started with in our in the dividend is what it's called. All right, we take that original power and reduce it by 1. All right, so instead of saying I had a power of 2, which is what I started with, I'm now going to have a power of 1. So I'm going to write an x to the first power here. All right, so I'm always taking what I started with and reduce it by 1. And that's going to give me my initial power for my answer. All right. And then from there, what we're going to do is decrease that power by 1 until every coefficient that we have has actually a denominator, has a variable attached to it, with the exception of the last one, because the last one is a remainder. All right, so that very last entry is a remainder. The hope is that that value would be 0. Doesn't always play out that way. All right, so I have an x to the first attached to my coefficient of 1. If I move to the right here, reducing that power by 1, I get x to the 0. And then I'll have my remainder tacked on at the end. All right, so I'm looking at a 1x to the first, which is just x, minus 2x to the 0th, which is just a minus 2, and then plus whatever that remainder is. So that's going to be plus the remainder divided by the divisor, whatever the divisor was. So in this case, it's x minus 2 plus negative 18 over x minus 3. Okay. It's a fairly complicated process, but the more you do it, the easier it is to kind of understand the process itself, and then therefore know that you're doing it correctly. All right, like I said, we're gonna do another example in a sec, but we do, after all of this work, want to make sure that we just did it right, I would imagine. So what we would do is we would type in the original division problem. All right, so I would just put it in as a fraction because division fractions are interchangeable. So x squared minus 5x minus 12, and then an x minus 3. Right, so that's what this graph would look like. Okay, you can put y equals f of x equals whatever you want, but it's really just the ratio that we care about. Then what I would do is type in my answer, x minus 2 plus the fraction negative 18 over x minus 3, and make sure that it gives you the same graph. All right, and it does, it maps to the same location, turning them both on and off. You know, you could do the whole thing like I was doing before, where you make one of them a dashed and, you know, a little bit thicker than the other, so it kind of stands out a little bit more. But it's a good way to verify your work, because again, you do all this stuff and you want to make sure that you did all that stuff right. So like I said, we'll do another one. So we have x squared plus 3x plus 2, which can also be thought of as 1x squared plus 3x to the first plus 2x to the 0. All right, we strip that down to just the coefficients, 1, 3, and 2. Separately, we look at the denominator. We're going to take that denominator, or the divisor, and set that equal to x minus r. And we use that to solve for the value of r. What's going to happen is the x's cancel. We get 2 is equal to negative r, which means -2 is equal to positive r. That's the number that goes outside the little L division bar kind of thing. So we put a -2 on the outside. We carry down the leading coefficient, which in this case is a 1. We multiply that 1 by the number on the outside. And that'll give us the next entry in the synthetic division table. 1 times -2 is -2. We'll add that to the existing number in that column. So the -2 gets added to the 3, or 3 plus -2. Either way you want to think about it, result is going to be a positive 1, which in turn gets multiplied by that value on the outside, giving us 1 times -2, result -2. If we add that to the existing value in the table, in that column, -2 plus 2, or 2 plus -2, gives a result of 0. So this is an instance where we have a remainder of nothing. All right. So we started off with a power of 2. Our answer will then have a power of 1. So x to the first, or at least start off with a power of 1. All right. That 1 that I've highlighted in yellow, that's really a positive 1. So I'm going to tuck in a positive sign there. Our powers decline as we go from left to right. I start off with a power of 1. Our next one will, and it'll turn out to be our last one, will be x to the 0. But if I started off with an x to the 5th, and then I did my synthetic division, my answer would start off with an x to the 4th. There's always going to be 1 less than whatever you start with. All right. So then I can represent this in a couple of ways. I could say x, 1x to the first is really x, plus 1x to the 0th is 1. And I can say, remember, it's remainder over divisor. I could say plus 0 over x plus 2. But 0 over anything is really just a 0. So this is the same as saying x plus 2. All right. If your remainder is 0, it's supposed to be like a little asterisk. If the remainder is equal to 0, then the divisor is a factor of the dividend. All right. I mean, in more lay terms, that's really the same as saying if the remainder is equal to 0, the bottom is a factor of the top. It's essentially telling you that you can come up with factors of a polynomial without being strong in factoring. If you remember that, like you had the trinomial and you had the 2 binomials, and you had to figure out, all right, well, is it a 2 and a 3 or is it a 6 and a 1? Right? Yeah, GCFs and all that. Synthetic division can be a substitute for that approach. All right. The last one I'll do, and then I'll let you go, is the next one because it's a little juicier. We have 3x to the 4th minus 11x to the 3rd minus 8x to the 1st. So it seems like something's missing along the way here. 8x to the 0th. All right, that 8 tacked on at the end, x to the 0th would be its multiplier. All right, but we're missing a power of 2. So we would rewrite.
Professor, wouldn't it be 8 minus 18x?
Oh, 18, thank you. Appreciate
No problem.
it. So I would rewrite this as 3x to the 4th minus 11x to the 3rd plus 0x squared minus 18x to the 1st plus 8x to the 0th because we have to account for every power between the highest power in our polynomial and 0. All right. And the only way, if the x squared disappeared, the only way that could have happened is if it were multiplied by 0. All right. So if you have any missing powers, we have to assume a coefficient of 0. All right. So if we strip this down to just the coefficients, it would become 3, -11, 0, -18, and 8. All right. Then we look at the denominator. X minus 4, we set that equal to x minus r. All right, the x's would then cancel. Happens every time. Every time that it's x minus or x plus something. If the leading coefficient is something other than a 1, then it's a different story. All right, so -4 is equal to -r, which means that +4 is equal to +r. So that's the number that goes on the outside. So we're going to bring down the leading coefficient. We're going to take that number and multiply it by the value on the outside. 3 times 4 gives you a 12, which we're then going to add to the existing value. The 12 added to the -11 gives you a 1. We're then going to take that 1 and multiply it by the number on the outside. In this case, that gives us a 4. We're then going to add that to the existing value within the table. 0 plus 4 is 4. We're going to take that 4, multiply it by the value on the outside. 4 times 4 gives you a 16. Add that number to the existing value in the table. Gives you a -2. That -2 gets multiplied by the value on the outside, giving you a -8. Add that -8 to the existing number in the table. It gives you a result of 0, which is the best case scenario. Remember, that last entry is going to be your remainder. We look at our original dividend, the numerator, and we say, okay, that started off with the power of 4. I'm going to reduce that by 1, which means my answer is going to start off with the power of 3, so x to the 3rd. The 1 and the 4 that's in my solution area, those are positive numbers, so I'm going to put a positive sign in front of each of those. The negative ones already have signs, so I'm not worried about those. I'm starting off, my answer starting off with the power of 3, reduce my power by 1 as I go from left to right. So the next one would be power of 2, power of 1, and then finally power of 0, making sure that I've accounted for every power between the highest power, which would be power of 3, 1 less than what we started with, and the power of 0. All right. Then clean it up and you'll have your answer. In this case, 3x to the 3rd plus x squared plus 4x minus 2. And that would be what you would get if you were to divide that original 4th degree polynomial with 3x to the 4th minus 11x to the 3rd and so on by x minus 4. Divide those two, you get this result. All right. If you're not sure, again, just like we've been doing, you type in the original.
Professor, the one that says x minus 4 equals x minus r, right? Or the square root.
Say it again, sorry.
The x minus 4 is x minus square to the root, or is that an r?
That's just an r.
Okay.
All right, so here's my original function. And then I would just be checking to see if my solution gives me the same graph. If it does, we're good. If it doesn't, then I start looking for my mistake. It does, so we're good. You know, if you're not sure, you turn them both off, you turn them on one at a time. These are definitely the same graph. All right. So I'm going to put a star on the next problem, so you can give that one a shot on your own. We'll start off next class with that problem, and then we'll get into the remainder theorem, and then get into some other applications of this stuff. That's interesting stuff coming your way. All right, so let me stop the recording.